Hello, and welcome to Lecture 4 of Electric Fields in Phys 1204. In this lecture, we're going to start getting more quantitative as we look in more detail at the fields due to charged particles. We've already seen the expression for the field due to one charged particle in an earlier lecture, and so I'm not going to go through it in detail again. I am just going to quickly recap it, and in particular highlight some issues of the notation we use. So if you'll recall, we got the expression for the field due to one charged particle starting from Coulomb's law, which is not telling us about the field, it's telling us about the force that one charged particle exerts on another. And so in this case we have a probe charge, QP, near some other charge Q, and we're interested in the field due to Q. And note that there is an r hat QP, which is a unit vector pointing in the direction from Q to QP, or we could equivalently talk about an r hat QA, which is exactly the same vector, but we're just naming it that because it's pointing from the charge Q to the point A where we're finding the electric field. And now the definition of the E-field simply tells us that we take the force on our probe charge and divide by the charge on the probe charge, and that will give us the electric field at the location of the probe charge. And so, as we've seen, the field due to charge Q simply comes out like this. By the way, I will occasionally, sloppily, refer to this equation as Coulomb's law. That's not really correct. It's not Coulomb's law. Coulomb's law is about electric force, and this is telling us about electric field. However, this equation is a direct consequence of Coulomb's law. We get it from Coulomb's law in a single step. Just a few quick points about notation, and in particular the various position vectors that come up. So the field due to a charge QS at some point P is given like this. And note I'm not bothering to talk about a probe charge anymore. We've seen how that works out, and we can now just quote the answer of how the field due to a point charge will come out. So it depends on this radial vector, RSP, where I call it a radial vector because no matter where point P is, this vector points radially outward from QS to P. Note that that comes from, in any coordinate system we wish to define, the position RS of our charge and the position RP of the point P where we wish to know the field. Those, of course, depend on our choice of coordinates, but the radial vector is a relative position. It is the position of P relative to the position of the charge. And so, like any relative position, it's independent of our choice of axes. But we find it from those positions just through a usual vector subtraction. Just verify that if you go negative RS plus RP, you come up with RSP. And the distance RSP that appears in the equation for the electric field is just the magnitude of that vector. And I'll just remind you, as we saw in the previous unit, that we can get a unit vector like RSP hat just by taking RSP and dividing it by its own magnitude. I want to get on to working some examples, but the one remaining thing I need to remind you of before doing that is that when we have multiple sources, such as multiple charges, then their E-fields add together to give the total E-field. And remember that this is a vector sum, and so in a case like this where we have three source charges and we're interested in the field at P, we can think about each of those source charges as producing a field of its own, and the total E-field at point P is the vector sum of them. And note that that vector sum, while you can find it algebraically, the real meaning of this sum is a picture like this, where we're putting the individual vectors head to tail to get a total. This is general. It applies no matter what sort of source each of the sources are. But if they are all charged particles, then we can substitute in the expression we got previously for the E-field due to a charged particle. Let's work an example and find the electric field at this point P due to this pair of charges Q1 and Q2, where I've given the amount of charge on each and I've given their positions. And here is the position of the point P. And you'll see that this goes very much like the calculation of the electric force on a charged particle due to two other charged particles that I did in Unit 1 of the course. But remember, we're not calculating a force here. We're calculating a field at P. There is no object at point P to feel a force. We're calculating the field, which gives us an easy way of calculating forces on particles that might pass through point P. So I'm going to leave many of the details of this to you. I'm going to skip through it rather quickly so that you can follow along. So the field at point P is going to be a vector sum of two fields. There's going to be some E1 due to charge 1 and some E2 due to charge 2. And the total field at P is going to be just the vector sum of those two contributions. And we know how to find those two contributions using the expression that we've already found. We will need here the sizes of these vectors r1p and r2p. And you can get r1p vector and r2p vector either by the appropriate vector subtractions using these vectors we already know, or in fact you can just read them straight off the diagram, right? Over 2, up 2, over 4, up 2, that tells you what those vectors are. Once you've found those, you can find the r hat vectors using the usual trick. We can now quickly get the magnitudes of these two relative position vectors, where note now I'm working in meters, and we can then write down the unit vectors quickly. Now we just have to collect all that together and put it into our expression for the E field. So here it is, and I'll leave you to pause the video and look that over in detail. And it comes out to this expression, and as is so commonly the case, I'm more interested in the units than anything else. So let's look at the units. We have Newton meter squared per Coulomb squared times, and each of these expressions is in coulombs per meter squared. And so the meters squared and meters squareds cancel, and these coulombs take out one of these coulombs, and we get newtons per coulomb, which is the usual unit for an electrical field. Note, it is a force per unit charge at the location. Notice how big this is. We've got an answer that's of order 10 to the 5 newtons per coulomb. But just think about this. These charges are of order 10 nanocoulombs, which is what we saw before is a reasonable charge for, say, charging up a ping pong ball using plastic rod that we've rubbed or something like that. So these are very modest charges, and we're looking a few centimeters away from them. And so this is telling you that the fields close to something like a charged plastic rod can be of orders 10 to the 5 newtons per coulomb, or very similar, rather large numbers like that. Just think of what that means, though. It means if you put a charge of a whole coulomb there, it would feel a force of order 10 to the 5 newtons. But a whole coulomb is a gigantic charge. More typically, the charges that you might have moving by this would be of order nanocoulombs or so, and so we get very modest forces. An important special case is the case of an electric dipole, which is just a pair of charges with a total charge equal to 0. And if you think back, you'll see that you've already seen the electric dipole because I used it as an example in a previous lecture when I was drawing E-fields. Electric dipoles are very important in a lot of other courses you'll take. They're very important to chemists because many molecules have permanent dipoles. They're very important to engineers for a variety of reasons. For example, a dipole antenna is just an oscillating electric dipole. So we're going to say that the charges are separated by some distance d. And I'll leave it as an exercise. Perhaps it would be a good assignment question, or it might be a good exam question, to show that anywhere on the x-axis with this choice of axes, the E-field is given by this. And you can just see from the way the individual contributions to the field, E plus and E minus, add together, that the total E-field here must be down, or in the negative j hat direction. It's useful to define this vector r minus plus, which points from the negative charge to the positive charge, and so it's just dj hat. You can see the dj hat right here. And so if we now define this thing that we call a dipole moment, all the chemists watching this have come across the idea of a dipole moment, though you might not have known what it is. The dipole moment is just the charge, the magnitude of charge on either of the charges, times this r plus minus vector. Then we can rewrite the E-field this way. Just a note of caution, we're calling the dipole moment p vector, which is the same symbol we use for a momentum, but it is most certainly not a momentum. Sorry about that, we've just run out of symbols long ago, and so we're having to reuse symbols. It's a good exercise to derive this expression, but what I want to do right now is talk about what happens as x gets very large. In other words, as we look at places where x is much larger than the distance between these two charges. Notice that when x is very large, this expression in the denominator is going to be approximately just x squared, because if x squared is much bigger than d over 2, you can basically ignore this part. And so that tells us that at large distances from the dipole, the E-field goes as 1 over x cubed. You can see that. We can simply replace this expression with x squared, and we have x squared to the 3/2, which is x cubed. And the absolute values are necessary because whether we're on this side of the axes or on this side of the axes, the E-field points down, opposite the direction of the dipole moment. The details of the results of this are not what's important. It may be very useful to you in a future course in chemistry or, say, antenna theory, that E-fields due to dipoles fall off as 1 over the distance cubed. But that's not really important to us now. What's important to us right now is to start to get used to this sort of reasoning process, which we're going to see more and more of in the coming lectures in this course. In particular, it's useful to think about why this field falls off as 1 over distance cubed. We know that the E-field due to an individual charged particle falls off as 1 over distance squared. So why does this one go as 1 over distance cubed? Well, each of the contributions, E plus and E minus, are falling off as 1 over distance squared. However, if you think about how they are oriented relative to each other as you look at larger and larger distances from the dipole, you see that they get closer and closer to pointing in exactly opposite directions. And so they're canceling each other out to a larger and larger extent. That's why the dipole field falls off faster, 1 over distance cubed, than the field due to an individual charge, which falls off as 1 over distance squared, because there's this extra cancellation going on.